Separable first-order differential equations. Our objective is to solve a separable first-order differential equation. Let's start by reminding ourselves, what is a first-order differential equation? Remember, differential sounds like differentiable, which means derivative. So a first-order differential equation is an equation that has a first derivative in it, like dy dx equals a function of x or y or both. A separable first-order differential equation is a differential equation that can be separated in order to integrate. So it looks like this. Dy dx equals m of x divided by n of y, such that we can separate it to look like n of y times dy and m of x times dx, where we're multiplying a function of y times dy and multiplying a function of x times dx for the purpose of being able to integrate. Let's take a look at some examples of separable and non-separable differential equations. This is a separable differential equation. Dy dx equals x times y, because I can get the y to the dy side using multiplication. I can divide by y, or I can multiply by the reciprocal, 1 over y, to both sides. And then I can get rid of the dx by multiplying by dx, so that the x is not on the y side, and to the other side as well, of course. Then I can get dx out from the y side, dx divided by dx, and the y out from the x side, y divided by y. That gives us 1 over y times dy equal x times dx. And now we have separated as a function of y times dy equals a function of x times dx. We would be ready to integrate. This one looks similar to this one, except since we're not multiplying x times y, the only way to separate the x from the y is to subtract the y, and then I don't have a function of y times dy, but rather dy dx minus y. So this is not separable because I cannot write it in that form. In the next example, dy dx equals x times sine of y. Because the x is multiplied to this function of y, I can do something similar to what I did up here, which is divide by sine of y or multiply by 1 over sine of y to both sides. Just like I got rid of the dx before from the y side, I'm going to multiply by dx to both sides. That gets rid of the dx from the y side and the sine of y from the x side. Notice that I'm not moving the dy because I need to have the dy in the numerator such that it's multiplied to the function of y. So this separation looks very similar to that one, 1 over sine of y times dy equals x times dx. This one looks very much like this, except because the x times y is caught inside the sine function, there is no way to get this y to that other side on the dy side. This one is separable. Even though it looks like we're adding x plus y, we're doing it in an exponential function. This exponential function can be rewritten as e to the x times e to the y, using our properties of exponents, because we know that when we're multiplying numbers that have the same base, the exponents get added. So e to the x times e to the y is e to the x plus y. So now I can separate by dividing or multiplying by the reciprocal, the 1 over e to the y, and similarly multiply by dx to get it to the x side. So I've got the dx gone from the y side and the e to the y gone from the x side. So this turns into 1 over e to the y times dy equal e to the x times dx. I'm ready to integrate, except usually I want to think of the exponential function not in the denominator. So this would be better written as e to the negative y times dy equals e to the x times dx. In this one, e to the x times y, the way you can think of that using exponential properties is e to the x to the y, and there is no way to separate that to be a function of y times dy equal to a function of x times dx. Let's look at some examples. Find the general solution to the following differential equations. Then find the particular solution using the given boundary condition. So I have this differential equation, dy dx equals 3xy squared. I'm going to start by separating it so the y is on the dy side and move the dx over to the other side. I'm going to divide both sides by y squared, or rather multiply by the reciprocal 1 over y squared, times dy, and then I'm going to multiply by dx, so 3x times dx. Now I have a function of y times dy and a function of x times dx. Now I'm ready to integrate, although I'd rather bring this up to have the negative exponent. Y to the negative 2 dy equals 3x dx. Now I can integrate both sides. Using my power rule on the left side, I get y to the negative 1 divided by negative 1 equals 3 times x squared divided by 2, and then my collective plus c. Remember, I could do plus c on this side because I did an antiderivative, and plus c on this side, or I can just collect all the constants over here at the end on one side. Now I do have a general solution, but this is a really yucky way to write that, so I'm going to rewrite it without a negative exponent. Negative 1 over y equals 3/2 x squared plus c. Now, this is my general solution. Actually, both of these can be considered a general solution, just in different forms. Now I'm going to find the particular solution using the boundary condition y equals 2 when x equals 1. So for y equals 2 and x equals 1, I'm plugging in 2 for the y. Negative 1 over 2 equals 3/2 1 squared plus c. 1 squared is 1, so that's 3/2, and solving by subtracting 3/2, negative 4/2, gives me c equals negative 2. Now I can plug this back into here to get my particular solution. So going back up to my general solution, I'm going to write negative 1 over y equals 3/2 x squared minus 2, using that general solution and the c that I found from the boundary condition. This is a particular solution, but particular solutions can come in many forms. For example, I may need to solve this equation for y for other reasons. If I do, I might start by multiplying by 2 that's in that denominator so that I don't have any extra fractions. So if I multiply both sides by 2, then I get 2 times negative 1 over y, which is negative 2 over y. 2 times 3/2 is 3, and 2 times 2 is 4. This is another version of the particular solution. And then I can take the reciprocal of both sides, or multiply by y, and divide by 3x squared minus 4 to get y equals negative 2 divided by 3x squared minus 4. The point is, I have many ways to write the particular solution, starting with this one, that is the particular solution, or rather it is a version of the particular solution, but so are all of the rest of these that are particular solutions. Just be careful to note that the general solution is the solution that has the c and no derivative. The particular solution is the solution that doesn't have a c anymore and no derivative.